So good morning, everyone. And thanks to Professor Jagat Babu for presenting the first session. So what I will do is I will actually pick up from where Professor Jagat Babu has left off. And I have a fairly long presentation. So I see that we are already at 12 o'clock. So what I will try to do is, try to stress on those areas which are important and probably not touched by Professor Jagat Babu. The other areas, I think we'll either skip or, we can just gloss over it. So without further ado, let me start off. I'll this is an agenda, the rough agenda of what I intend to speak about. And parts of it have been touched upon by Professor Jagat Babu, introduction and background. And I would actually also spend some time on, the building blocks of Industry 4.0. And Professor Jagat Babu had mentioned about 8 technology or slash areas. And I have a similar kind of, the building blocks and also what is called the important thing called the smart factory concept. So we'll stress on that. And then after that, since this topic is going to be more about analytics and stuff like that. So what I'll do is I will also try to spend more time on the big data analytics and some use cases. I hope I can, do justice during the, amount of time available. So without further ado, let me start. So I will not spend much time on this. My rough thing is that I'm a PhD from ISC Bangalore, and I also did a master's from ISC Bangalore, and before that a bachelor's in electrical engineering from IIT Calicut. So I have been, ever since my doctorate, I've been in the IT industry for close to 26 years. The last industry engagement was with, I was a group manager at IBM at Bangalore, and what is called a cognitive business division. Some of you may have heard about a product called Watson, which was a cognitive platform of IBM. So there was this group was basically working on consulting and technology support and stuff really, and also product related support for the Watson business unit. So I've also worked in companies like Hewlett Packard and Toshiba and Wipro Technologies. So let me just, without further ado, start out on the basic definition or a basic summary of what Industry 4 is all about. So as they say, it is a strategic initiative, and this was actually initially propounded by the German government. I'm told that this originated in the Hanover Fair of 2011 when a formal proposal came out for Industry 4.0. The goal was actually transformation of industrial manufacturing through digitalization and exploitation of potentials of new technologies. So I'll delve into more detail as we go along. So the key thing here, if you see in the last sentence, is it's about Industry 4 production systems, both aims at both flexibility and things like enable satisfaction, individualized requirements of customers and customized. Now, this will become a little more clearer as we go along in the presentation. So I will just quickly gloss across. Professor Jagat Babu had already mentioned this, but let me just quickly cycle through this as this is a slide which is taken from the Technical University of Darmstadt. And there again, they say that, essentially the 1800s was when the first, from manual work, the first rudimentary manufacturing processes was introduced typically in the textile industry. So you're talking of the rudimentary mechanization from manual labor to the mechanization part, and things like steam power, hydropower, steam power. And essentially you would have heard about things like IC, industrial combustion engine, etc. These were the what you call the enablers of the first industrial revolution. What came out of this was one of the key drivers was also improving the working conditions. Prior to that, it used to be pretty primitive, and this was, I would say, the first where there was some formalization of all this and a movement towards addressing working conditions. The second block here, it talks about industrial revolution, the stage 2, and there we are talking about things like what actually contributed to that was this electrification. The rapid rise of electrification enabled industrialization and mass production. Okay, so prior to that, it was still mass production. It was using mechanical artifacts, etc., for what do you call it, manufacturing. But then it was not really mass production. The second stage was basically electrification and industrialization. The third stage was when there's digitalization and introduction of microelectronics and automation. Excuse me, just hold on a minute, please. One moment, please. Hello. Yeah, the third stage of the industrial revolution was the incorporation of digitalization and introduction of things like microelectronics and automation. So you would have heard about this first PLC, program logic controllers. And so essentially what you're saying is these are programmable machines. These are not machines which are really fixed and rigid. You can actually program them to do multiple things in a flexible manner. So essentially you are talking of program logic controllers, etc. And these are program and configurable. So if you see the difference between the second one and the second one is also fairly rigid. Mass production lines, you would have heard about Henry Ford and the Ford Motor Company. There was this mass assembly lines, but the things where production system was fairly rigid. There was no flexibility on different products that could be manufactured, and also so that was one of the drawbacks of the second industrial revolution. The third revolution made it a little more flexible. There could be flexible manufacturing concepts started coming. That is, you could actually have nowadays the thing is that the customer and industry demands are such that there has to be customization in the sense that you cannot have a rigid line which only manufactures one particular type of product. You need to have flexibility. So for instance, if I were to talk about an automotive line, just if I were to mention things like, let's talk about example of Maruti, right? Maruti has so many different models, starting from Swift to Wagoner to Ertiga to whatever. You have so many different models. Now, what happens is that, and basically some of these foundational concepts came out from the Toyota Motor Company, where they talked about, in addition to things like lean manufacturing and all those things which came out, they also talked about meeting a very customizable kind of production, where the same line could basically produce different products in the same line. So there was flexibility of manufacture, so this was the primary thing which came out of the third industrial revolution. So primary thing is flexible production, and then you have programmable machines. The fourth industrial revolution is a different ball game. It's a builds over that. We are here talking about what is called smart automation or cyber physical systems. Cyber physical systems, what we're meaning is that this terminology will be explained further, but we're talking about cyber physical modular systems. And the main thing is that they are decentralized, as opposed to the previous stages were all more or less centralized systems, were driven top down. So here you're talking about something called decentralized autonomous systems, which can communicate with one another in a modular form. So let me just give you a brief here. Prior to third industrial revolution, there was a lot of one of the key things about manufacturing is that how do you reduce costs, right? How do you so there were things like lean manufacturing and essentially just-in-time manufacturing, all of these concepts. And also there is this outsourcing thinking about that if a particular geography is very expensive in terms of worker time of the employee costs, then one option was outsourced to a geography with lower cost. So these are some of these ideas which are experimented, and pretty much saturation had been reached, and there was no scope for further improvement on the economies of scale and the production improvements in margins. So here, this industry 4, as I said about cyber physical systems, connected over, let's say, typically wireless, autonomous systems, and they are essentially autonomous systems which can communicate with each other and essentially optimize the production flow. So that's the key thing which is coming about. There was a report which said that we're still fairly early in the cycle. It may take upwards of 2 decades to fully realize the benefits of the fourth industrial So essentially, I've already mentioned some. I'll quickly go through this. We are talking about global competition and a need for fast adaptation of production to the ever-changing market requirements in terms of products, etc. So essentially, you're talking about an approach which requires to marry both business and manufacturing process, and also the entire value chain. You're talking not just about the manufacturing process and the factory, but also things like suppliers, customers, logistics, etc. So you're looking at a holistic 360 degrees view of integration of business manufacturing system as well as the company's value chain. So as I already mentioned to you, technically the realization happens through what is called cyber-physical systems and industrial Internet of Things. Okay, and also essentially we are talking about at a modular kind of an approach where we are talking about cyber-physical systems as modules. These are essentially embedded systems, right? These modules comprise of embedded systems with a decentralized control, also known autonomous systems. So we can pretty much, it's pretty much and then you're talking of these systems, these myriad of systems are actually connected typically through production. These units are self-organizing among themselves. A group of them could communicate with one another and arrive at an optimal production, I would say, process flow. So this is one of the major potentials that exist with this Industry 4.0 framework. So let me, without ado, let me also get into a little more detail about it. See, it's not just the factory shop floor. There are many units which go into all this thing, right? There is factors of productions, labor, materials, machines, other inputs, etc. So many things. So essentially, you can view it in an abstract way as there is input from different types of inputs which comes in. A lot of transformations take place, and finally you get the output, right? And the output is not just a product. It needs to, if you look at a holistic view, it needs to come from the transformations and the input stage all the way to the output, and then finally till it reaches the end customer and the sale and the value is realized. So we are talking about things like to manage this complex ecosystem. There is a in the manufacturing jargon, there is also something called a manufacturing execution systems, which deals with more from the production and manufacturing part of it. Like it talks about job scheduling, planning, resource allocation, so many other things, usage of raw material, etc. That's all handled by the manufacturing execution system. Then for the business function, you remember I told you, we are talking about integration of the business process as well as the production processes. So we are talking about enterprise resource planning, ERP systems. Typically, you'd have heard of systems like SAP, Oracle financials, and so on and so forth. So these are two key drivers. You have one is the manufacturing execution systems, and you have the ERP system. Then you also have, you need to have what is called and seamlessly tying through all this is analytics and big data. At the end of the day, when you talk about data-driven decision making and planning, you need to have, this can only happen if all the systems exchange information, collaborate, work, process data, exchange information, and are able to orchestrate this whole production in a way which is more optimal and can support the requirements of the customers. So we are talking of self-optimizing industrial production process. So here, let me just pause here, because till now I've been speaking. I will just show you a video here. I hope it comes out well.
A vision of tomorrow's manufacturing, products finding their way independently through the production process. In intelligent factories, machines and products communicate with each other, cooperatively driving production. Raw materials and machines are interconnected within an Internet of Things. The objective: highly flexible, individualized and resource-friendly mass production. That is the vision for the fourth industrial revolution. A look back at history. At the end of the 18th century, the first steam engines and the intelligent use of hydropower revolutionized production. The late 19th century saw the rise of electrical engineering and mass production. The first moving belt conveyor was used as long ago as 1870 in the slaughterhouses of Cincinnati, Ohio. In the mid-1970s, electronics and IT began to expand rapidly into industry. Siemens developed the first SIMATIC. Production became increasingly based on computer-assisted controls. The fourth industrial revolution is still a vision. Experts believe that it will only become a reality within the next 20 years. In intelligent factories, everything is interconnected wirelessly. At the German Research Center for Artificial Intelligence in Kaiserslautern, this future can already be experienced right now. Research is underway here into exactly what the industrial production of tomorrow will be like.
Fabriken werden zukünftig aus Bausteinen bestehen, aus smarten oder intelligenten Bausteinen, wie man es nennen mag. Vergleichen wir das vielleicht mal so ein bisschen mit einer Lego-Steinwelt. Das heißt, wir haben standardisierte Bausteine, die wir hoffentlich relativ einfach zusammenstecken und zusammensetzen können. Jeder dieser Bausteine hat bestimmte Funktionalitäten und wir können sie zukünftig in einem solchen fabrikinternen Internet dann kombinieren.
A bottling plant for liquids, set up together with Siemens, is used to demonstrate the most important components of the intelligent factory of the future. Each bottle contains an RFID chip storing a precise description of how it has to be processed. Which liquid, which lid, and which label. At each station, the bottle communicates directly with the machine, telling it how it has to be processed. At the end, a computer checks whether the bottle has actually been produced as desired. Factories with networked machines and products are already in existence today. In the future, however, these hitherto self-contained systems will be connected together in a comprehensive network. All devices, machines and materials will be duly equipped with sensors and communications technology and connect to each other. These systems are known as Cyberphysical Systems. The highlight is that they communicate with each other and also control each other cooperatively.
Wenn Sie sich das Thema Industrie 4.0 angucken, dann basiert sie ja auf der Logik dieser Cyberphysical Systems. Das heißt, Sie haben autokrate selbst arbeitende Systeme, die sich optimieren und sich gegenseitig austauschen und dadurch letzten Endes Produktion optimieren.
Ja, die Vision sieht so aus, dass wir ein Internet quasi hinunterziehen bis auf die unterste Ebene. Das heißt, jeder Sensor, jeder Aktor wäre damit quasi ein Teilnehmer eines Internet der Dinge. Jedes Gerät hat damit eine eigene IP-Adresse, ist damit adressierbar in diesem Netzwerk.
For the customers, this means tailor-made products at relatively affordable prices. For industry, it means highly flexible mass production that can be rapidly adapted to market changes, because in the future, product life cycles will be even shorter. Another reason why it's increasingly important to depict engineering across the entire life cycle. Maintenance, for instance, is planned in from the very start.
Wir haben ja bereits in den 90er Jahren mit Totally Integrated Automation entsprechend ein Setup gewählt, wo unsere Produkte und Systeme sehr gut miteinander kommunizieren können.
At Corporate Technology in Princeton, a cyber-physical control is being researched even today. The vision, the control, and all linked sensors are connected to the Internet.
One potential scenario is enabling the PLC to react to utility pricing information in building automation. We can enhance PLCs to use simulation to calculate how much to pre-cool a building, with the ultimate goal of turning off the cooling system during peak times.
But that's just the beginning.
We've prototyped capabilities in a PLC to access big data in cyberspace in real time. And we've also enabled a network of PLCs to connect to a dynamic simulation of the entire physical process.
Siemens is shaping the future of industry. Connecting the real with the virtual world of production is making it possible to enter entirely new dimensions in quality, efficiency, and flexibility. The company is well prepared for Industry 4.0.
Good afternoon, everyone. First of all, I thank Dr. Sangeeta ma'am for giving such an opportunity to present this webinar. Then I thank today's two speakers, Dr. Jagat Babu sir and Dr. Venugopal sir, for taking such a wonderful class based on 4IR and data analytics in Industry 4.0. Then I thank each and every members who participated in this webinar and make this webinar a grand success. Once again, on behalf of Mechanical Engineering Department and Computer Science and Engineering Department, Vedavyasa, we thank each and every participant for making this session a grand success. Once again, thank you all.